All right, welcome DS25 to module 3 of our linear regression sprint, right? We're going to continue our discussions from Monday and Tuesday, but to me, today is where linear regression starts to get more fun. It gets a little bit more complex. Monday and Tuesday, we were fitting regression models where we just had one y variable and one x variable. Also, one dependent, one independent variable, right? Other names for x and y variable, right? Well, today, we're going to start adding more x variables to our model, right? And try and really make a model that is encapsulates all of the most important aspects of what predicts y, right? And we're also going to look at measures of model fit, right? To see, okay, what percentage of the y variable is our model explaining? And we'll learn how to kind of test things out, put in some variables, see if they help, see if they improve our model. If not, remove them, right? And kind of be able to experiment to build what we call a parsimonious model, which means a model with just a few features, but that explains why as best as possible with just a few features, right? We're not going to, the opposite of a parsimonious model is sometimes, colloquially called a kitchen sink model, where you throw everything into your regression, including the kitchen sink, right? And you just see what happens, right? And that's actually an alternative way of going about what we're doing today, right? Is to put everything in and then remove the things that don't work, right? Until you get to a good model where we're going to work at it in kind of the opposite direction and put things in little by little, because that'll just help us be able to better understand some of what's going on as we add X variables. It'd be a better way for learning things here, but both methods can work, right? And again, I just want to reiterate that this week we're focusing on building linear regression models that help us better understand the relationships between these X variables and the Y variable. We may also use them to make predictions, but prediction is not our number one priority, right? Our priority is interpreting those slope coefficients and understanding what do they say about, what are the determinants of interment time, right? Or how long these bones have been buried for. What are the determinants of dreaming sleep, right? That's the question we want to answer this week. Not so much, oh, how can I best predict the absolute most accurately dreaming sleep or interment time, right? If that was our absolute goal, we might lean a little bit more towards the kitchen sink model, right? Because at the end of the day, our goal is not interpretability. We just want to make a model that's as predictive as possible, right? So we're going to approach things from a slightly different angle when our goal is inference as opposed to prediction, right? And so this week we're coming at it with an inference type lens, right? So just know that you may use linear regression with it slightly differently if your goal is prediction and nothing else. If you don't care about understanding your model at all, you may not be quite as diligent as in your experimentation and some of those things that we're going to do today. All right. So let me go ahead and share my screen. All righty. So again, we are looking at using multiple predictor variables, multiple X variables, right? This changes our model. A linear regression model that uses multiple predictor variables we call multiple regression. One that uses just one and one XY variable we call simple regression, or sometimes you'll hear it called bivariate regression. Okay. Again, we're going to keep on using t-tests to determine the significance level of variables as we add more X variables. Are those variables actually significant? Is their slope non-zero? We're going to keep on thinking about that. But we're going to also look a lot at this measures of goodness of fit, including R squared and adjusted R squared. And those are going to be kind of our North Stars, in addition to the p-values of our t-tests about, have we improved the model, right? We're going to look at them heavily. So again, I want to return to our kind of forensic data here. Import long bones, drop the NA values and the oil flags, right? And get back to some of the things we had talked about yesterday, right? So the null hypothesis between, if we're comparing nitrogen and time, the null hypothesis for the t-test that's being run here states what? Does it state that the two variables are related or unrelated, the null hypothesis. Okay, I've got a response from Hector. I want at least 4 responses in the question thread. Awesome. Okay, unrelated, right? Similar to the chi-squared test, right? The alternative hypothesis is that they are related. So in symbolic notation, we know that if our beta 1 coefficient is 0, right, then that's saying that the slope of that line is 0, that x really doesn't have any influence on y or is not correlated with y, right? There's really no relationship between the two. Likewise, the alternative hypothesis is that our beta 1 coefficient, our slope coefficient, is not equal to 0. Okay? So let's run this model. And you've done this probably a lot of times by now. And you even tried out some other things, some other variables with our sleep data, some log transformations. And we'll get to those a little bit later today. Let's look at them. Okay. So we're going to say that model equals OLS, right? That's the function we imported. And we give it this funny string with time tilde nitro, okay, our column headers. Our data is long bones. And then we call .fit to calculate the model.params and the model summary. And then we can print the model summary to get our results. Okay. Now, today, I want to, yesterday we talked a lot about this center section, which is probably the most important section of this output here. A strong contender for that most important is these two top lines right here in the top right section. This is where we see the R squared, right? Sometimes also abbreviated literally R squared. It's related to the correlation. However, do not confuse those. This R squared here has a capital R, right? And the common correlation coefficient is represented with a lowercase r. They're not exactly the same, even though they do share some mathematical relationships, okay? Well, what does this R squared value represent? This is a measure of what we call goodness of fit, right? So you can think about goodness of fit. I'll show you some examples here as being how closely do the data points fall to the line, right? So here on the left, you see that the residuals are larger. The data points are not quite as close to the line. This would have a worse R squared compared to this guy on the right. So the guy on the regression on the right is going to have a higher R squared. The regression on the left will have a lower R squared. Okay. So our R squared values will exist between 0 and 1. The closer to 1 means the better our model fits the data, and the more far away from 1. Here's another example, okay, with actual numbers here, which is what I was looking for. Okay. If our data points fall exactly on our regression line, well, then our R squared is going to be 1, or we'll sometimes hear this also in percentage terms, 100%. Right? If it's a pretty good fit, there's a strong amount of linearity here, it might be around 80%. The more spread out might be 40%. If it's really, a shotgun blast with a line through it, our R squared might be around 0%. Right? I don't think this is actually a great example of R squared that 0%. I bet this is a made up number, but so we want this to go between 0 and 1, and we prefer a higher number, right? And we'll often turn those into percentages as we talk about it for reasons that I'll explain here in a second. Okay, so the interpretation of R squared, this is very, very important, and I think will help you understand why we're going to look at this measure as kind of our guiding principle for have we improved the model, okay? The interpretation of R squared is the percent of variability in the Y variable that is explained by differences in the X variable, okay? Now, you could think about variability in the Y variable to be roughly equal to like information, like the amount of information in the Y variable that's explained, or the amount of signal in the y variable that's explained by the x variables, right? It's basically of all the things that determine interment time, what percentage of those of the things that determine interment time have we captured with our x variables, right? You can think about it kind of that way, right? Now that's a loose statement, but something that can guide your thinking, right? So this is why we'll often take these decimals and turn them into percentages as we interpret them, because it literally means the percent of variability in the y variable that is explained by the differences in our x variables, right? And so in our case here, our r squared was 0.45, right? Let's see. Okay. The interpretation is that 45% of the variability in interment length is explained by differences in nitrogen composition of the long bones. Okay, and that's actually pretty decent for a simple regression model, right? Just having one x variable, that's a decent amount of kind of explainability, if I can use that word, right? Going on. And we're going to try and increase this R squared value as we go up. Okay. So sometimes you'll hear this said, if we have multiple X variables, we won't say that, oh, 45% of Y is determined by, or 45% of interment time is determined by nitrogen composition. You'll just say, oh, 45% of interment time is determined by, or is explained by the model, right? If you use lots of X variables, you sometimes won't hear them like stated individually. You'll just say the model in general of all the X variables we've included, right? Because we're going to start to include more than one here in just a minute. So, however, you know, the opposite of this is also true, right? This means that 55% of the variability in interment time remains unexplained by our model, right? So there's still more things that we could learn about interment time that we are not capturing with our current model, okay? So as a reminder here, we are going to make our scatter plot and look at this, because I want you to get a feel, a little bit of an eyeball feel for what does a 45% goodness of fit look like. Now, as we add more X variables, it'll become more and more challenging to plot these regression lines, okay? Which is part of the reason why we started and introduced this topic to you with just one Y variable and one X variable, because we can actually graph it and see it and learn about it. But as we add more X variables, the graphing does become more and more challenging. Okay, so here is our graph. And you can see here that there's still a fair amount of variability outside of our regression line, right? These points have, some of them have somewhat large residuals. Our confidence interval that we looked at was still somewhat large, right? There's improvement to be made, okay? So the big question is, right, how do we address this unexplained variability, okay? Well, in ways I've already alluded to, let's see if some of the other variables can help us understand why skeletons with the same nitrogen composition have different interment times, okay? Right, so nitrogen composition has already captured some of the meaning here, some of the signal. We want to see, can we find something that is influencing interment time in addition to, that is unexplained by the nitrogen levels, right? Something that we're not currently capturing, all right? So we're going to do this by taking our simple linear regression model, turning it into a multiple regression model, and adding additional variables or X variables to our equation here, right? Notice there's a dot, dot, dot here on the end. You could add as many as you want in theory, okay? Now you probably want to have some justification for doing that, but you could add as many X variables as you want, and you'll still be able to the math will still work. You'll still be able to calculate the parameters. Okay. When we do this, we have multiple slope values that get calculated, right? Notice we just keep on adding betas. We have beta 0, beta naught, beta 1, beta 2, beta 3, beta 4. You can go as far as you want with beta variables here, right? So as we add a second x variable, we're going to be looking at beta 2 instead of beta 1. And when we do a t-test, we're going to do a t-test with a null hypothesis that beta 2 equals 0 rather than beta 1 equals 0, right? So just adding a different beta for each variable, okay? So let's do this. And we are going to look at, if we look at our long bones data set here, right, you'll notice that there are some other variables, other columns of our data set that we have not used, right? Right now we're using nitro to predict time. Oil is no longer useful to us, so we can't use that because we've removed all the ones in that column. This is just a column of zeros now. But we could still use depth, lime, and age. We probably won't use site very much today, but we're going to try some of these other ones and see how it helps the R squared, or the goodness of fit. Okay. So we're going to start off looking at the lime variable. And like a good statistician and data scientist, we're going to do a little bit of exploratory data analysis. Before we do this, we're going to make a graph. All right. You'll see me going back and forth between the LM plot and the reg plot here, but they are quite similar in their functionality. However, I like the LM plot. It gives us this hue parameter where we can color the data points based on the values here, right? So for example, if I'll finish this line in a second. If I take my long bones and look at the lime column and do value counts, long bones with a B, okay, it'll show us that some of these coffins were buried with quicklime and some weren't, okay? This is what we call a binary variable, a dummy variable, also an indicator variable. It just indicates was quicklime used or not in the burial, right? Maybe this has some meaning beyond the nitrogen content that could tell us about interment time, okay? So we're going to color our data points based on whether or not they have lime in them. And I'm gonna turn off the regression line here for a minute. Oh, this should be Y, not T for time. I was trying to think about typing time. Missing requirement keyword data. All right, so data equals long bones. We forgot to include that. It's kind of a lot of parameters. Okay. And then you should have a collective right? Like this is striking, right, in a way. Sometimes your categorical variables, your binary, your indicator variables won't be this, there won't be this clean of a separation between them, right? This tells us that for basically any bodies in our data set, any skeletons that have been interred for longer than about 60 years, all of them used quicklime. That must have been something that was used more often 60 or more years ago, right? But more recently was not used, right? So maybe this variable can tell us something about interment time. You can see automatically that it does, right? That if quicklime was present, it's older. If it wasn't present, it's younger, right? So maybe this can capture something about interment time that the nitrogen content alone can't already tell us. Right? So let's do it. Let's include this in our model, right? So sometimes you will see in regression models that when we finally know exactly the name of the variable, right? We won't just include X, but we'll say B1 nitro or B2 lime, right? And we'll actually use the column header as well to indicate, okay, X1 is nitro, B2 is lime. It's just another way of being a little bit more explicit when we write out the equation to say what each of these X values refers to. Okay, but notice we've just added another beta 2 that's going to represent lime. Okay, and when we do this, we're going to run a new t-test to see, is lime significant? Right, when we include this, is its slope non-zero? Is there really a relationship between interment time and lime? Right, so again, our null hypothesis is that beta 2 equals 0, and our alternative hypothesis is that beta 2 is not equal to 0. Just like yesterday, but for a different, we're testing a different slope coefficient. Okay. Then we will write out our model. Okay, and this is going to be a little bit different than what we did yesterday, or well, both Monday and Tuesday. So we have time, that's our y variable. Remember, we always say that first here. Tilde, and then nitro. That's what we did before, but then we're going to use a plus sign here to separate the different x variables, right? So I could put lime in here. However, this lime variable is categorical, meaning it's only got two potential values, whether a 1 or a 0, if lime was present or if it was not, right? And so when I'm including a categorical variable here, I will type this capital C and then put in parentheses the variable. And this is going to tell stats models to treat this data slightly differently due to its categorical nature. And I'll explain how it's treating it differently here in a minute. Okay. So let's run this and let's look at the model summary. Oh, I forgot to do something. What is my model missing? You may have done something like this on your assignment. Okay, so I'm missing data equals long bones. And I'm also missing one other important thing. It says, OLS object has no attribute summary. Yeah, I have not called .fit, so the model summary has not been generated until I call .fit on my model, right? So it says, hey, there is no summary. What are you talking about? But then once we call .fit, then there is a model summary. Okay. So now we see that lime appears in the model. Okay. Because this is a categorical variable, right? T.1 here indicates that this is the coefficient for when lime was present. Okay. So this coefficient is relative to the baseline of there not being lime, right? So this is saying that if there is lime, right, then we would expect that variable to be at least 25 years older, or the interment time to be 25 years greater, right, compared to not having lime, right? But that's the important thing here about these categorical variables, is that these categories, we had two categories, 0 and 1. The 0 was left out here. We're only seeing the coefficient for if lime was present versus if it was not present, right? And then this coefficient is relative to lime not being present, right? Okay, so 25 years older if lime is present, or 25 years longer interment time on average. Okay. We also see that our p-value here is 0. It says that lime definitely is related to interment time. Okay, and we see that our r squared has gone up. Okay, it has gone up by quite a lot, actually. This is a pretty big jump, and even this r squared is decent with just these two variables. Is pretty good r squared for having just two x variables. Okay, so these two things together tell us this was a good inclusion. Right, we've added something to the data that has improved our model, and we're capturing more of all the things out there that could explain interment time. We now are representing, around 76, 77% of those things. Okay. So let's write out our model here. Okay. But one thing I want to mention that might get a little bit tricky, and something I want you to watch for on your assignment, is we included these variables in the order time, nitro, and then lime. But down here below, we have intercept, lime, nitro, right? They're not necessarily in the model summary in the same order that we provided them in the string up here. And you'll see that this order down here is also reflected in the model.params. Okay, so just know that the order of model.params is not necessarily reflective of the order in which you put them in the string up here. Okay, so be careful about that. Always double check kind of the model.params to make sure you're grabbing the right value or the value that you think you're grabbing from it. Okay, so our intercept is 180.5, we'll call it. We'll round these to one significant digit or one decimal place, plus, or excuse me, minus, because we want to have nitro first. That's our beta 1. So minus 35.6. So that's times nitro here. And then plus 25.5 times line. Okay. And y hat here again means our predicted values, right? This when we're working with this regression line, these predicted values will all fall exactly on the line. Right? Why we use that hat character there. Okay. One thing I want to point out here is that a lot of the other coefficients have also changed, right? And if we scroll up above and we look at the regression when we used just nitro, right? Our intercept was 316, okay? And our nitro coefficient was minus 69, about minus 70, right? Well, all those things have changed here a little bit, okay? Our intercept is now 180. Nitro, its coefficient has dropped quite a lot. And lime here has a coefficient of 25, right? So what is sometimes said here is that maybe there was a little bit of overlap. Maybe time told us a little bit of the same information that nitro also told us, and then soaked up is, you'll actually hear that phrase said, soaked up some of the coefficient from nitro and from the intercept. Right? At the end of the day, we have to account for 100% of the regression line here, right? So you will sometimes see the other coefficient and coefficients change as we include a new one, okay? So here's the big question is like, does that mean our interpretation when we only included nitro is wrong? Well, no model is perfect. We're not trying to make a perfect model. We're trying to make a useful model, okay? But this tells us that once we account for some other factors, or maybe you'll sometimes hear it, once we control for lime content, maybe nitro cannot be attributed with quite as much of an influence on interment time, right? Each gram of nitrogen decay does not change interment time as much as we would have thought previously, right? This is another reason why including multiple X variables improves our model. It improves our understanding of some of the other variables that we've included as well, right? And of the coefficient, right? This coefficient is creeping towards it's creeping towards the range under which we would maybe be a little bit more comfortable interpreting it, right? Again, this is if lime is 0, if there's no quicklime used and there was no nitrogen, right, then this is the interment time. And you notice it's dropped significantly, and it's getting closer to a number that is present within our actual data, right? So maybe we would start to get more comfortable interpreting the intercept. Right? So a lot of things can change, okay? Each of these additional X variables will hopefully improve our model overall, and we will know that by the p-value and the r-squared. Okay. I want you to think about, however, what this equation is saying and what has actually happened to our regression line as we include this lime variable. Okay. So I want to go through a couple of scenarios, right? What the model is actually done, and this might be unintuitive for a minute, is the model is setting up a set of parallel lines. There's actually 2 regression lines now, okay? And this is why I say it gets more complicated to graph things as we add more x variables, right? One for when lime equals 0, and one for when lime equals 1. And to show you an example of that, right? Imagine when lime equals 0. Well, what would happen here? Here's my equation, right? If lime equals 0, then this is, there's no value for lime. We're just multiplying 24.5 times 0, okay? So this whole lime term goes away. And we end up with one single line here, right? So this is a regression line at one point, okay? Well, then if lime equals 1, well, this will be 24.5 times 1. So essentially plus 24.5, right? And we'll have a different line. Let me, that is 24.5 units higher, right? So we're just taking that line and we're shifting it upwards by 24.5 units. Because if you think about it, this line value, all that it does is it gets added to the intercept. It's as if we took this intercept and turned it into 205.92, right? If I took this value and added it to the intercept. Right? So I end up with one equation here with one y-intercept and one equation here with a y-intercept. Oh, goodness me. That is 24.5 units higher, right? So I end up with 2 regression lines that are parallel to each other, but one is shifted upwards to capture those 2 different categories, okay? It looks something like this, right? You can imagine we might have data points throughout this, but we'll have parallel regression lines cutting through the same cloud of points. Okay. Let's look at how Seaborn generates this. Now, Seaborn's graph is not exactly what I'm describing here, but it might give you an idea about what I'm talking about. Okay. This is what Seaborn does. Okay. However, you'll see that these lines are not exactly parallel. It's because Seaborn is not quite exactly following the same process that we have here. Seaborn is taking a subset of the data. It's taking the yellow points and fitting a regression line. And then it's taking the blue points and fitting the regression line. Whereas we fit our line for both at the same time, okay? But you can see that they're mostly parallel, and there's one line for the skeletons with quicklime and one line for the skeletons without, okay? So again, the graphing is a little more complicated. The interpretation is a little bit more complicated here. However, right, our predictability has improved, right? Look at the distance between the data points and the regression lines, right? On average, the residuals are quite a bit smaller with these regression lines compared to our original, right? By splitting it up in this way, the quality of fit or the goodness of fit has improved. Now, R squared is increased, right? We're able to get predictions that are closer, more accurate in this way as well, right? Because this regression line is closer to the data points on average, okay? So I think this is a pretty cool thing, right? Our model has improved in basically every way. The only way it's slightly maybe more challenging is it's more challenging to interpret, right? Because some amount of it is attributed to nitro, some amounts attributed to lime. We've got multiple regression lines going on, right? It's getting a little bit more complex, but it is a better model, okay? So when we have a model with more than one feature, we talk about each one being significantly associated with the target after taking into account the effects of the other variables, right? So we're saying that, right, with our p-values here that were both significant, we would say now that we've included multiple x variables that lime is significant after taking into account nitrogen content or controlling for nitrogen content. Or also, we could say it the other way as well, that nitrogen content is significant after controlling for the use of quicklime in the skeletons, right? So It's after we've already, controlled for all the other X variables in our data set. Is nitro saying something beyond what is already captured by the other X variables? And yes, it is, right? That's what our p-value is telling us. Okay. However, I want to talk about R squared a little bit more and add one wrinkle to our interpretation of it. Okay. Sorry for my scrolling here, but we have R squared, but down on the line below, we see this thing called adjusted R squared. You say to yourself, well, what's the difference? They're almost the same number, but not. Okay. Mathematically speaking, for every X variable that we add to our regression, good, bad, or ugly, doesn't matter if it's a useful X variable, a terrible X variable, the R squared will always go up. It will always go up. Okay. And this is problematic. Like, we don't want this indicator of, the quality of our model to always improve, even if we've added something that's really not very useful. Okay. And so the adjusted R squared is a little bit better. Okay. What the adjusted R squared tries to do is it tries to include a penalty for including an additional X variable, right? So we take the original goodness of fit and say, hey, if you're just including tons of X variables, that penalty is going to be large, right? So that's why we see a somewhat of a small difference here, is because we've only included 2 X variables, right? So our penalty is not large, but we want each individual X variable to improve our goodness of fit by like a certain amount relative to the others, in order for us to say, okay, yeah, it's made a big enough jump, a big enough improvement that we're going to keep it. So now that I've introduced this topic to you, from now on, we are going to look at almost exclusively just the adjusted R squared. Okay, R squared's good. Adjusted R squared is a little bit better in that it does not always go up, irregardless of the variable we've included. Okay. So let's talk about that R squared. Okay. And then we will take a quick break. Okay. So in the model with just nitrogen composition, what was the adjusted R squared? So scroll way up to our other model summary. Well, it was 43.3%. Get back down to it, right? We'll say that this is 43.3%. And in the model with both nitrogen composition and burial with quicklime, the adjusted R squared was 76.2%. That's quite a large jump. Okay. That is a huge, right? Huge what? There's a huge increase in predictive ability, right? We're explaining a lot more of our Y variable now than we were before. Okay. So now that we've introduced R squared and the ability to include multiple X variables to our data set, we're going to take a break. And when we come back, we're gonna start experimenting with other things. What if we include this X variable? What if we include in that X variable? We're going to create something called an interaction term, be able to include those, right? What if we log normalized the variable and then included it, right? It's like a lot of things we could do to experiment with the model. So let's take a 5-minute break and we'll continue when we come back. All righty, come on back. We'll get going again. We're gonna start experimenting with some more variables here. So let me share my screen. Okay. Can we do even better? What if we added a third x variable? We're gonna add a variable about the depth of the burial and see if the depth of the variable can impact interment time. Okay. Again, we're going to test with our p-value, our hypothesis test, whether or not the slope coefficient is 0 or non-zero, right? And we'll include this again by adding the plus sign here and saying depth to our model, right? It's not a categorical variable, so we don't need this categorical indicator. Okay. And we'll call .fit and look at the model summary, okay? And here's what I want you to do before I run this code cell. I want you to check in with your intuition and your understanding of the world, okay? Do you think that burial depth would be related to interment time? Okay. Has the depth of burials increased and decreased over time? Is there any correlation there? Have humans always buried them, you know, their dead, their loved ones at about the same depth, right? Like, do you think that there's anything about burial depth that would tell us about interment time? And I want you to give me a guess. Do you think that depth will be significant or insignificant, right? Tell me in the question thread. I want your best guess before I run this code cell. Will depth have a significant impact on or kind of explanatory power here with interment time? John says no. Curtis says insignificant. Andrew says no. Okay. Kyle says yes. Okay, going out on the limb. Ben says significant. Jerry says significant. Okay, so we're a little bit split. I've got 3 no's and 3 yeses so far here. Let's take a look at it. All right. First thing, did our adjusted R squared increase or decrease? 75.5 versus 76.2. Ooh, slight decrease in adjusted R squared. Okay, that might tip us off about what we're going to see here down below. Depth here, coefficient, close to 0, right? And p-value, pretty high. Okay, what does this tell us about burial depth? Okay. What does this tell us? Okay, so think about that. In this case, we see that we fail to reject the null hypothesis. And we conclude that after accounting for nitrogen composition and burial with quicklime, burial depth is not associated with interment time. Yeah, so it's actually not a significant factor once we've already accounted for lime and nitro, right? So we will choose to not include burial depth in our model of interment time. Our best model remains the same as it was above. Okay? So basically, this guy right here, however, without burial depth. Right? That really got messed up somehow. Oh, I'm missing a couple of $signs here around my betas. So this is still our best model. Okay. Let's try one more. Let's try including age. Okay. That's going to be our new beta 3, right? Because we're not including burial depth anymore. Okay. So let's add age on and see what happens now. Age. Same thing. Not really making an improvement here. Our adjusted R squared went down yet again, and our p-value is high. Again, we fail to reject the null hypothesis. And we conclude that after accounting for nitrogen composition and burial with quicklime, age at time of death is not associated with interment time. The adjusted R squared also decreases as when we added burial depth. Okay. So notice our R squared did go up. Okay. R squared will always go up for each additional X variable that we include, but the adjusted R squared went down, telling us that this was a weak X variable that had little to no relationship with interment time, okay, after accounting for lime and nitro. One thing I want to point out here is that what if I did an OLS model only using age, right? Not lime, not nitro, just age and time, okay? What would I see? Look at this. Age is significant, okay? It is a weak predictor, but it's a predictor, right? But look at my adjusted R squared, okay? This is explaining less than 10% of what's going on with my Y variable. Less than 10% of the variability in interment time, right? So when it's included on its own, it may appear significant. However, the things that age says about interment time are also already captured by lime and nitro, right? Which is why we include lime and nitro. They soak up almost all of the effective age, and it becomes insignificant, right? Which is just because a variable may seem significant in a simple regression model does not mean that it should necessarily be included in the multiple regression model. Okay. Most variables will be significant when they're on their own. Okay. We've got to include better control variables because I want to know, does age matter in addition to nitro and time, right? After I've controlled for nitro and time, does age say anything in extra that wasn't already captured by those two? You could think about, imagine we were fitting a regression and we wanted to predict your annual income, okay? And we wanted to know our beta 1 coefficient that we're primarily interested in is what is the effect on income of obtaining one additional year of schooling? Okay. You go to another year of school, how's that going to impact how much you make? Okay. What are some of the things we might want to control for if we could, assuming we had them in our data set, we want to include in this regression to account for? Because, for example, there's a lot of things we want to control for, and we want to know that that 1 year of schooling is helping in addition to some of these other things that are explaining income, right? What do you think are some of the things in this kind of theoretical regression I'm explaining to you we want to explain? We want to know the impact of one additional year of schooling on income, but there's what other X variables would we want to include? What do you think? Hector says GPA. Okay, maybe you got an additional year of schooling, but you didn't get a lot out of it, right? Maybe you flunked out of, or almost flunked out of your classes. Andrew says the cost of schooling. Did you go to a private school, a public school? Is this a university class? You're in university, right? Curtis says, yeah, job growth for that year. Maybe there's things going on in the economy that affect your income besides schooling. Okay. There's all kinds of things. We might want to control for your gender, your socioeconomic status, the income of your parents. Did you do extracurricular activities when you grew up? Where do you live in the country? Where do you live in the world? Right? Like there's a lot of things that we would want to account for because I want to know, does that additional year of schooling change your income after we've accounted for really everything else we can think of, right? This is, you'll sometimes see lots of X variables included in regression models as for no other reason than as to control for other things, right? So we've accounted for everything we could think of that might affect income, right? And now once we add one additional year of schooling, income goes up by $2,000 or something like that, right? And we know that like one additional year of schooling does move income, right? Because if it doesn't, then it's maybe says that maybe some of those other things included in the regression are more important than getting one additional year of schooling, right? And this regression that I'm explaining is actually problematic in a couple of ways we won't talk about today. It's something that's been studied extensively, but is actually a really tricky thing to nail down because there's a ton of things that affect your income, a ton of them. And to control for all of them appropriately is tricky, very tricky, okay? So let me go ahead and share my screen here. And when I talk about one other kind of variable that we can include that will help us control for what we call interactions between two variables, okay? So up above, when we added this categorical variable of Lyme, we got parallel regression lines. Well, what if I didn't want my regression lines to be parallel? What if I wanted to allow them to not be parallel, something similar to what we're seeing here, or maybe even cross one another, okay? That is a possibility with these interaction terms that we can add to our regression line, right? So you'll see something like this, right? In addition to what we call our main or additive effects, right? Things like Lyme and depth added to the model of plus signs. Those are just regular things that we add on, okay? Just our a plain X variable. We can also test for interaction effects. For example, should the lines describing the relationships of nitro to interment time be parallel, or should they each have their own slopes, right? And this will even allow them to cross if needs be. So the way that we will do this is we're essentially going to multiply two things together, nitro and Lyme, right? And I want you to think about, what does that mean? If I multiply them together, what does it really mean if these two things are interacting? It means, well, is there some specific behavior of Lyme, of nitro when Lyme is 0 as opposed to when Lyme is 1, right? Does Lyme being a certain way change the behavior of nitro, or does nitro being a certain way, like a low level of nitrogen or a high level of nitrogen, affect how the Lyme interacts with things? Like, are these two things causing each other to behave differently in a specific circumstance, right? If I want to know how these two things interact with one another, this interaction term will try and capture that. And then, graphically it allows them to take on different slopes, okay? So let's run this and take a look at it. And we see that not really significant. And our R squared again, our just R squared is not the highest it's been. It would be higher if we just didn't include this term. This tells me, right, that the effect of Lyme on interment time is not really related to, or is not really affected by nitrogen content, and vice versa. Nitrogen content is not really affected by the presence of quicklime, right? If there was some interaction between X variables, I could account for it in this way, but we're seeing that there's not a huge impact here. And look how wide our confidence interval is, right?
I've got a question.
Value's not so small. Go ahead, Chris.
All right, so scroll back up to the graphs you had right there, like the 6 of them there. All right, well, if they're not parallel, like it's a thing with lines, right? Eventually they're going to cross anyway, somewhere on the graph.
Yep.
So and that would come down to like scale. I mean, they might not look exactly like any one of those given examples, but if they're not parallel, they're going to cross. And what I'm getting twisted up on is when we're adding these extra lines, we're adding them to the equation or the function of y hat, right?
Yep.
Okay, but then if you're talking like so we're talking like we're going this, here's x and here's y. Oh, yeah, hang on.
I'm pitting your screen so we can see you big.
Yeah, yeah. Hang on. Okay. Oh, well, never mind. It like here's X and here's Y, or here's our graph, right?
Yeah.
Well, then when we're adding in these other variables, though, we're saying that this line is changing, you know, somehow, right? But when we're adding extra dimensions, aren't we adding another vertical X, Y, Z, and then?
Yeah, technically we are. Technically we are.
But I mean, when then we're looking at this data though, and we're looking at this data, and but we're still trying to represent that or think about that in a 2D plane.
Yeah, so let me show you something that might blow your mind a little bit. Okay. And don't get too far down this rabbit hole, because as we add X variables, it becomes more challenging to graph. Let's see. And some different things can happen. Okay. Sometimes if we have a binary variable, we'll get parallel lines like this, and we can still graph that on, you know, on a two-dimensional plane. However, let's see if I can find a good example here. Sometimes when we add multiple X variables, we end up not with a regression line, but a regression plane. If we, if we truly graph this in 3 dimensions, right? One for X, one for beta 1, one for beta 2, and one for Y, right? And so technically, once we add additional X variable, if we wanted to graph all of the X variables at once, we would need 1 additional dimension of space to do it. All right. What you're seeing here, when we graph things on a 2-dimensional plane, we're excluding some of the other dimensions, right? It's just as if I was taking like a cross section of this, right? And only looking at that specific cross section. Does that make sense? Or if I was looking at it directly from one side on. Okay. So yeah, whereas, I like your intuition that spatially, as we add X variables, we're literally adding kind of dimensions to our regression plane. That is one way to think about it. But this may get you twisted up in knots, and this becomes almost impossible to graph once we add a 4th X variable, right? A 4-dimensional graph is like, your mind explodes trying to think about it, right? Which is why I don't necessarily want you to think about it this way. Well, I mean, I do and I don't, right? I don't, if this is gonna just confuse you, then I don't want you to think about it that way. But imagine, so these different 2-dimensional graphs are slices of that larger multi-dimensional graph. Right? Since if we're only looking at it from one dimension on. So if I was looking at this, instead of at an angle, if I was looking at it just like I was looking down a tube, right? At the one side, that was having one side be directly flat to me, that would be like the scatter plots we're seeing here. And then I could twist it, and I could look at, the other side and look at that straight on, and then I could look at it from the top straight down, right? I can this is called projecting it from a 3-dimensional space into a 2-dimensional space, and we can still do that, but we're going to end up with multiple scatter plots with regression lines in them as we add more and more X variables. So again, it gets more complicated to graph, but it is possible to look at it with 2-dimensional scatter plots. Does that help a little bit, or does that just open up a giant can of confusing worms? Okay. So we don't really have interaction effects here, at least not that we are seeing strongly present. Okay. Let's see. Trying to follow my notes here to make sure I don't miss anything. Okay. So we do not see interaction between nitro and lime. So based on the data we have, the best model to predict interment time of a skeleton is, yet again, same as this one above, still our best model, right? We've tried other things out, and we're still Still here. Oh, I didn't even need to copy it. It was already written out for me. Okay. One thing that you might be thinking about as we get to this point in the lecture, it's like, well, am I going to have to try out all the different combinations of all the X variables that I have and try out all the interactions between all those variables? And then maybe some of them I'll want to log normalize, and I want to include the log normalized versions and the interactions with the log normalized versions of the normal variables. And then, like, what if my data set is not just 7 columns? What if I have 50 columns or 100 columns, right? That's an unfathomable number of combinations to have to try out, right? There are, well, and that's not even accounting for other feature engineering that we could do. Remember, we used a ratio of body size to brain size yesterday, right? That was kind of a form of an interaction. Lots of different things here that we could do. And yeah, it becomes really big and gnarly. And this is another place where your computer can't tell you what's right, right? You as the data scientist approach this with some domain knowledge and some intuition and, you know, your understanding of the world, and you try and make a regression model that is both has significant values, but is still parsimonious, right? It's small, right? We're not going to include terms just for the heck of it. We're going to include terms purposefully, right? And really have a reason for doing so. Okay. There is a branch of data science called AutoML, stands for automated machine learning. Okay. Where there are algorithms that will try and automate some of this model selection for you. They'll automatically do feature engineering. They'll try out a whole bunch of combinations of feature engineering. They will automatically run many regressions for us. However, this is something we want to be careful for, because the p-value we're looking at is we're using a 95% confidence interval, right? So we're only confident 95% of the time. That means 1 out of every 20 times that I run one of these hypothesis tests, I will get unlucky and get the wrong result, right? So if I'm running 400 different regressions, okay, or a regression with 400 different X variables, what's 400 divided by 20? Well, 20, right? I would expect there to be 20 X variables in there that appear significant when they're really not, right? So sometimes I can trick myself into thinking that there's more things here that are significant than not, just by including a lot of terms or running a lot of regressions. This is something that's called p-hacking. And this is something that's done on accident when people aren't aware of it, but sometimes unfortunately done purposely because people are pressured to publish research papers or things like that, right? So we want to be a little bit cautious and not just go and run tons of different regressions of all the different combinations. We want to try and approach it with some kind of a purpose, some kind of a theory of our own or understanding of the world that's guiding us as to what we should include, what we shouldn't include. Okay. All right. So going back to our best models so far, time, nitro, and lime as a categorical variable. Let's generate a prediction with this current best model. Okay. And so for X1, we want to try this out with, remember, X1 is our nitro, right? So we want to say, okay, what would the interment time be if we had 3.88 grams of nitrogen? Okay. And a body that was not buried in quicklime. So it'll be a 0 for quicklime here. We'll grab our model params. I think this should be in the right order, right? And then we'll generate our predicted value, right? So we estimate that this body has been buried for about, and I think, yeah, for about, I'm actually going to double check the model params. Let's look at this. We'll do this in a different code cell. And this says that intercept is 0. Okay, so we had, we said that X1 was nitro, but slope 1 comes from lime. Okay, so I actually got them mixed up. This is why we have to double check the model params. So what was it that tipped me off that this was maybe wonky? Well, I got a prediction that seemed silly, seemed outside of the range of my data, right? It shouldn't be, I shouldn't be generating predictions in this range because my regression lines, these are normal inputs, right? These are inputs that are within my data set. So this prediction should also be similar to the interment times in my data set, but it was way off. And that caused me to question if I was using the right things here. So let's swap these two. Actually, I'm going to leave this the same. I still want nitro to be first and lime to be second. I'm going to swap these model params. I'm going to say that slope 1 should be nitro and slope 2 should be the presence of lime. Okay, 42.24 years. That seems a little bit more normal, and it's actually the correct prediction here. Okay. So we estimated this body has been buried for about 42 years. Okay, let's do one again here. All right, same thing here. I'm going to make sure I grab the right model params. Okay, but we're going to use a different nitrogen content, and this body was buried with quicklime. Right, so a 1 here for quicklime. Right. So what I really wanted to show here is that now that we have multiple X variables, we're going to have multiple inputs when we want to generate a prediction. Right, we're going to have X1 and X2. And we have to feed those both into our equation, right? Then add the intercept to get our y hat, our predicted value. Okay. But this predicted value, it's going to be on a different line, right? Because quicklime is 1 as opposed to 0, right? So this is going to be on the orange line instead of the blue line in my Seaborn graph, right? And we say this person has been buried for 78 years, right? Now, higher, right? A little bit higher here, okay? So one thing I wanted to show you here, let's run a third model just for kicks. But I'm going to do this model with exactly the same nitrogen content, but without quicklime. Okay? I just want to show just the difference of having versus not having quicklime. Okay? And what is the difference between these two? What is the difference? Well, the difference is just the coefficient, right? Do we have lime or do we not have lime, right? If we have lime, well, then we're going to say it was about 23 years older. This might not be exactly 23 years, right? But like it's in that ballpark, right? We're seeing the presence of lime versus not presence of lime. We jumped down, to the lower regression line with this prediction, and we were up on the upper regression line with the one on the top. 2 parallel regression lines. Okay. So I already talked about this. What happens if we have like lots of features, thousands of potential features? Well, again, we can't try out every possible combination of regression. So we've got to think about it ourselves. We can't just try everything, right? We want to avoid doing that, okay? But we also run into something that's also a little bit problematic called the curse of dimensionality, okay? Now, this XKCD comic might be how you start feeling a little bit in Unit 2, okay? Right now, we're trying to be principled in our approach. It says, this guy standing on a pile of numbers and data, and he's got a box to hold answers in and a funnel, right? It says, this is your machine learning system. It says, yep, you pour the data into this big pile of linear algebra and then collect the answers on the other side. What if the answers are wrong? Well, you just stir the pile up until they start looking right. Well, if it didn't improve the model, just take it out. Put something else in, right? Try something else. Just stir it up, right? You might feel like this a little bit. You'll probably feel like this a lot more in Unit 2 than you do right now, okay? which is why some of these things like that Logan shared, you know, the AutoML stuff has, why do I have to stir it up? Why can't I let an algorithm stir it up for me? Right, kind of thing. So we'll talk more about this in a minute. Okay. So what the cursive dimensionality is really all about is if we have more features than observations. Okay. Well, what is another synonym for features in a model, right? Well, this is variables. But when it comes down to my data set, this is columns of my data set, right? If I have more columns in my data set than I have observations or rows in my data set, then I may run into this problem of the curse of dimensionality. Okay. The curse of dimensionality means, right, when I include a new feature in my model, like line, right? Well, then my model got more complex. It became parallel lines with interaction terms they could cross, right? If I were to include logarithmic or exponential terms, then my regression lines could actually have some curve to them, right? They could fit nonlinear shapes, right? And so if I include tons and tons and tons of x variables, okay, I'll show you a graphic here that I like. Right? Each of those adds some new complexity to my model, allows my model to twist and turn, right? And if I have a lot of x variables, my regression could theoretically be something like this, right? Where instead of fitting the general trend to my data, trying to get a good prediction, my regression line is being pulled off track by individual data points, right? And it's twisting and turning and trying to have the best goodness of fit, right? It's trying to be as close as it can to each of the data points. Well, if I include a lot more x variables than I have data points, well, now it can fit to individual data points. And this is really bad. We're going to talk a lot more about this graph in Unit 2 and problems with overfitting. We can also have the opposite problem, underfitting. Notice that the R squared here could definitely be better, right? If we included some a quadratic term maybe and had a U shape or something like that, like we could fit this data better, right? So this is a model that is not complex enough relative to the number of data points that we have. And this is a model that is too complex relative to the data points we have. We'll sometimes say that it's memorized the data, right? It knows it goes exactly through nearly all of the data points, okay? So more complexity, more dimensions to our model allows it to fit more complex data and more complex patterns in data. Sometimes this is a good thing, but we can go way overboard with it, all right? Overfitting is one of the primary challenges that we face when we're using machine learning models, is trying to avoid overfitting, because we want to use complex models that can find complex relationships in the data, but we don't want them to memorize the data, okay? So there's a few ways we can kind of fight back against this curse of dimensionality. And again, you will absolutely have this problem if you have more features, more x variables in your model than you have rows of data, right? So here with the long bones data, if I had 35 or more x variables, then I will overfit, right? My predictions will have this problem, okay? So that's kind of a lot. But maybe not if I'm including lots of interaction terms, doing a lot of feature engineering, et cetera. Like my number of x variables can grow pretty fast. So what we're going to do if we have, this is, by the way, like a rule of thumb that I'll say is try and have at least 5 times as many rows of data as you have columns of data. 5 times as many rows of data as columns of data. Now that's a general rule of thumb. It's not a perfect rule, but that is one big way to avoid this. I'm going to actually add that on here as a number 4. And it's not really columns of data. It's really variables in your model, right? Maybe our original data set only has 7 columns, but then after feature engineering, we end up with 10 or something like that, right? So 5 times as many rows as variables in your model, okay? Other things we can do is eliminate variables that are not related to the outcome, right? And this is what we've done already. We saw that burial depth and age weren't really related, so we're not including them, right? And that's decreasing the number of variables we include in our model. Okay. Another thing we can do here is combine variables using feature engineering. You may remember way back on the second day of class, we looked at some housing data and we looked at the price per square foot, right? Well, that price per square foot included information both about price and about the square footage in one single variable. We did something similar yesterday when we took brain weight and body size and we divided them to create a ratio of brain size to body weight. Well, that's one variable that now includes information about both of the two previous variables. Right? So that could be a way that we can kind of reduce the number of columns that we're working with. Okay. Last but not least, we can use things called dimensionality reduction techniques. You will learn more about these in Unit 2. A popular dimensionality reduction technique is something called PCA, or Principal Component Analysis. That's what the acronym stands for. Basically, what PCA is going to try and do is it's going to try and take all of our columns of data and squish them down, summarize them in as few columns as possible. Okay. And you may say to yourself, how can it do that? How can it take all these columns and squish them down into less columns? Well, it's really a kind of a complex thing, and it's hard to wrap your head around. PCA, some students say they're as confused the third time they study PCA as they were the first time they studied PCA. It's a complex thing. What I want you to know about it is we have this big trade-off when we use PCA, right? We take all of our columns down and we squish them down and we generate a new data set. However, that new data set loses almost all of its interpretability, right? We know we still have a whole bunch of information from the previous columns, but I can't point to any one of the new columns in my new PCA data set and be like, ah, that is the nitrogen column, right? Because it gets combined and mixed up with a whole bunch of other things, and it's a smaller data set. I've reduced the dimensions or the number of columns. And again, this goes back to CT's question, right? When we add a new X variable, aren't we literally adding, another dimension of space? Yeah, in a sense we are, which is why this is called dimensionality reduction. Okay, trying to reduce the number of columns we're working with. But if you are using linear regression, and your goal is to be able to understand the relationships and be able to go, oh, nitrogen, 1 additional gram of nitrogen increases interment time by 24 years. If you want to be able to say a sentence like that, you will not use PCA, because PCA makes statements like that almost impossible, right? It is used for improving the predictive capacities of our model, but we lose all of the interpretive capabilities, right? So it is used almost exclusively for predictive models, where that is the end all be all, and that's our only goal, okay? But it is a tool we can use to fight back against this curse of dimensionality. And there's many different dimensionality reduction techniques. This just happens to be one of the most popular, okay? So just something I want you to be aware of is that is a problem that can arise with any kind of machine learning model, but linear regression is particularly susceptible to the curse of dimensionality, right? One thing I want to talk about here before we get to the sleep example, right, is you've seen that linear regression fits linear data, or we can transform that data and say, take maybe curved data points and straighten them out so that we could fit a straight line through them. We could also look at it the opposite way. If those points are still in their same shape, we could imagine that the regression line is curving. You could look at it either way, right? But one thing that is going to be a theme that carries through our machine learning discussions is this concept of fitting non-linearities in data, right? Linear regression is pretty good. It can capture the linear relationships, right? But not all patterns in data are linear. We saw this with correlation, right? That there was a whole bunch of patterns in the data with correlation. Let's see, where was it? The correlation independence here, right? We looked at this image that showed us, hey, correlation and linear regression, they can capture linear forms of data, but what if my data looked like this, or like this, or like this, or like this, right? So now there's a few of these we could capture pretty well, right? If we feature engineered a quadratic term, then we could get our regression line to bend in a quadratic-like shape. Maybe we could feature engineer like a sine wave, or a polynomial term that could turn and twist throughout this point, right? We could capture some of these nonlinear shapes with linear regression, okay? But it becomes, the more nonlinear the patterns in our data are, the more complex our model has to become, okay? One thing I want to point out here is this is why neural networks are hyped up so much. Okay? Neural networks are complex models. They fit nonlinearities really well. They also have a high tendency to overfit, and they're very susceptible to the curse of dimensionality. We need a lot more data when we're fitting neural networks than when we're doing linear regression. So I just want to point you to this cool page. I just want you to be excited about where we're headed in the future, and how the things we're learning today are really going to carry over into stuff we do in the future. So there's a thing here called TensorFlow Playground. Okay, and I'll share this with you because I think it's a pretty cool thing to play around with. And you can, just using the GUI here, the graphical user interface, you can make your own linear regression, excuse me, your own neural network model. Okay, and check this out. This neural network model, okay, it's a neural network. This is the simplest form of a neural network I can create. When I just have one layer and one node here, it's called a perceptron model. A perceptron literally is linear regression. Okay, the simplest form of a neural network behaves in exactly the same way as linear regression. Okay, so I'm going to run this, and I want you to watch what happens over here on the right-hand side. Now, this model is trying to classify these data points, but I want you to see the shape that is determined. Okay, notice how the boundary between these two things is a straight line. Straight line. It's because it's behaving, or trying to behave, like a linear regression. It might be a little bit more apparent if I switch the data set to something like this. As I add another y variable, or a second x variable, well, now my linear regression can move in both the x direction and the y direction, or something like that, right? We're still, this is a linear regression with multiple inputs, right? Don't take this analogy too far, because once we start adding many hidden layers and many neurons to these layers, right, the relationships to linear regression go away, right? As the complexity here increases, it's definitely not linear regression anymore. But this added complexity is going to help my model fit non-linearities in this data. Look at this data. How would you put a linear regression line through this to classify it? Like, I don't know, like it's very non-linear. Okay, I don't know what polynomial term you would use to fit this data, but it would be wonky, right? But the neural network, over time, and over many what we call training epochs, right? You see, it's trying its best to curve around and to fit these non-linearities. Okay. And let me help it out a little bit more. Give it more neurons. I'm going to change the activation function to ReLU. You'll learn about that in Unit 4. ReLU tends to work a little bit better. And there it goes. You can see it's almost perfectly classifying here. Okay. So increased complexity means we can fit non-linearities, but then we risk, right, overdoing it. And that's really what the curse of dimensionality is about, is if you overdo it, you're going to overfit. You're going to have some problems, right? If you go crazy and just throw in tons of x variables to the point where you have more x variables in your regression than you have rows in your data set, you have overdone it, okay? And the ability to fit nonlinearities is a powerful thing, but comes with dangers and its own susceptibilities. Okay? So hopefully that gets you a little bit excited about where we're headed, and I hope that TensorFlow Playground thing is fun to play with. Okay? And kind of cool to know that the simplest version of a neural network or perceptron behaves exactly like linear regression. Kind of cool. All right. So with that aside, let's return to our sleep example here, and let's do some experimenting. Let's see if we can find out some other variables that make an impact on dreaming sleep. See if we can have a higher adjusted R squared, right? And be able to capture a greater percentage of the variability of all the things out there that could explain dreaming sleep. Let's try and account for more of them in our model. And by doing so, we will be able to make more accurate predictions as well. Okay. So we'll load this data set. And you'll remember that yesterday on your assignment, we had you do a little bit of feature engineering here. You made a log life and log gestation variables. Well, we're going to see if those are significant today. So we're going to make them as well. They'll appear over here on the right-hand side of our data frame. All right. And we'll start off with our two variables on their own, our log of gestation. Okay. We see that our adjusted R squared is about 0.3. Not terrible for including one X variable. And it is significant for now, right? But as we add more controls, maybe it'll become insignificant, right? We saw this with age, with the long bones data set. Okay. So far, so good. Let's add the log of life. Okay, the adjusted R squared has gone down. Okay, and gestation is still significant, but the log of life is insignificant. Okay, so think about this with me for a minute. Why do you think? Well, let's do a third one here. I think this will help us envision this. Let's do one with just the log of lifespan. An adjusted R squared of 0.12, not very great, but not zero. There's some amount of information here in lifespan. Significant, not exactly zero, but it's less than 0.05. Okay. How come on their own they are individually significant, but when put together, the log of life is the one that gets thrown out? Like why not gestation? Why is gestation not the one that becomes insignificant when we combine them? What do you think? What do you think? Okay, Curtis says the adjusted R squared didn't go up. Good, meaning that this combined model does not capture a greater percentage of the variability in Y compared to just using the log of gestation on its own. Okay. Went from 0.311 to 0.249. This really tells me something about the relationship between lifespan and gestation, right? It tells me that they're really saying kind of the same thing, right? That there's nothing that once we control for one or the other, like we're not, so really once we control for gestation time, lifespan isn't saying anything that gestation didn't already say about Y, right? And vice versa, right? So take a look at this. If I look at the correlation between the two, they're moderately correlated, right? Life and gestation. Okay. Now this is not the log versions, but that's okay. Right? And if I graph the two against one another, they're decently linearly correlated, right? So in a sense, these two things are so strongly correlated that they're more or less saying the same thing, right? They're kind of stand-ins for biological complexity or maybe even just the size of the animal, right? The bigger the animal, the longer the gestation. And the bigger the animal, the longer the lifespan. Or the more biologically complex, the longer the gestation period. The more biologically complex, the longer the lifespan. Those two things are providing the same signal, right, in my data set. So when we ran the regression with them together, log of life is the one that became insignificant because gestation had more signal to it in the first place, right? So the less important of the two is the one that became insignificant. And in fact, let's try something here. Let's reverse the order of them. Okay. Same thing, same exact stuff, right? So the order here doesn't matter a ton. Typically, we want to put the variable we're most interested in listed here first, okay? But the order didn't determine it, right? It was that the log of the lifespan was shared so much of its information with the log of gestation due to their correlation and them truly representing this more or less the same thing, that we kept the stronger of the two, okay? And the log of lifespan is the one that ended up appearing insignificant. Okay. Any questions about that? I realize that could be a little bit confusing here. Okay. This is something between our x variables that we call collinearity. Collinearity. If we have two x variables that are highly correlated with one another, then they could be saying the same thing. And when we include them, right, all of the effect gets soaked up by one or the other. The one that soaks it up still seems significant. The one that got soaked up, right, appears insignificant, right? So we call this collinearity, or sometimes multi-collinearity. You'll hear both of those terms used when we have x variables that are correlated with one another. Okay. Alrighty. Let's see. We've got 40 minutes left. There's one little demonstration I want to do if we have time here. So it looks like they are, again, moderately correlated with one another. If it was 0.8 or higher, we would say they were strongly correlated. Okay. They aren't really contributing separate information to the model. Once we control for one, the other one isn't really saying anything that we didn't already account for. All right, so what do? We include just the one with the highest predictive ability, and that's what stats models did as well, okay? And oh, I don't know why this is log life though. I thought we saw that log of gestational time was the best. Okay. So we'll keep on including log gest. That gave us the higher adjusted R squared. Okay, so the R squared is, let's see. Trying to make sure I didn't miss anything in my notes yet again. Okay. The R squared for gestational time, while not great, is definitely higher than the R squared for lifespan, right? And so we'll go with gestational time. We'll leave out lifespan for now. They're saying roughly the same thing. All right, but what about danger index? Let's take a look at this. So we have a few other columns we can play with here. One of them is this danger index. Okay, and so if we do sleep danger.value counts, we see that we have 5 different danger indices from 1 to 5. And if we had the data dictionary here, you would see that 1 is animals that are not in danger as often, and 5 is animals that are in a lot of danger. They're, this is a kind of a scale, a 5-point scale between are you the predator or are you prey, right? And 1 here is like these mammals are predators. 5 here is these animals get eaten all the time. They are in danger, right? And you can imagine, right? Again, thinking about this with our intuition first, right? If you're in danger a lot, you're probably not getting a lot of sleep, all right? Unless you know how to burrow or make a hole or climb a tree or something like that, you might be afraid to sleep for long periods of time. Okay, so let's see if this is borne out, that these danger levels really have an effect on dreaming sleep. Okay. We're also going to make a box plot here, right? Even more exploratory data analysis. And this box plot kind of already tells me there's something going on here, right? That we see animals with that are in less danger getting more sleep, and the more danger they're in, you know, these box plots are kind of descending, the means are decreasing. And animals in a lot of danger, they are not getting a lot of sleep, dreaming sleep at least. You know, less than 1 hour a night of dreaming sleep. Okay, so this definitely seems like animals who are in more danger get less dreaming sleep. Right? Hopefully I can see that with my eyeballs even before running the regression here, right? But this is a categorical variable. Remember, categorical. We've got 5 different values here. It is not continuous. So what we're going to end up with is 5 different regression lines. 5 different regression lines. They're all going to be parallel to one another for the increasing levels of danger here. Okay. So Seaborn, if we graph this and we color the hues based on danger levels, you see that they're kind of all over the place. All right. We have gestational time and sleeping, right? We have some animals who have long gestational times that are in a fair amount of danger, and we have animals with low gestational times that are really not in danger, right? So this is actually a good thing, right? It's good to see that gestational time is not really correlated with danger, right? Because that means that these danger variables might say something different than what gestational time is already saying about my data, right? Maybe I'm going to capture some aspect of what determines sleep that I have not captured yet. Okay, so the messiness of this is actually maybe slightly a good indicator for us. So we're going to include these danger columns using the C for category, right? And then wrap danger in parentheses. Okay, and we're going to get an output here for each of the different categories except for one. Okay, remember we had 5 danger categories, but we only have 4 coefficients here. Okay, when we use categorical variables like this, the danger level 1 has been omitted. It has been left out of the report here, and you can imagine that it's 0, right? And the coefficients for these other categories are relative to the danger levels of, or the sleep levels of level 1, right? So from level 1 to level 2, right? Animals in danger level 2 get 1.2 hours less dreaming sleep than animals in danger level 1. And animals in danger level 3 get 1.5 hours less sleep on average than animals in danger level 1. Again, this coefficient is with respect to danger level 1, right? So animals in the highest danger category get 1.8 hours, almost 1.9 hours less dreaming sleep than animals in danger category 1. And something a little bit odd has happened here is that, like, it looks like animals in danger category 4 get more dreaming sleep than animals in danger category 3. It's a little bit interesting here. This could be a thing. This could be just random variation with our sample, right? Maybe if we had more data points, this would straighten out, and this would be always decreasing. Okay. Let's look at the plot here with the regression lines and the danger hues. It's pretty messy, and these ones again are not parallel, right? Ours are going to be parallel. This is Seaborn trying to fit independent regression lines. Okay. Okay. So again, to come back up here to fill this in a little bit, we're going to say the predictability of the model is, well, our R squared, or just R squared went up a fair amount, right? Is improved by adding the danger index. Now the adjusted R squared is about 0.5. We'll round this up to 0.5, right? About 50%. So with the danger index and gestational time, we could predict about 50% of the information or the signal in dreaming sleep. Okay. So that's good. This is an improvement. Because the coefficients are all negative numbers, we can see that a higher danger index corresponds to less dreaming sleep. Okay. Now we ask ourselves, is it possible that there's an interaction? Okay. Is it possible that gestational time and danger levels influence one another, right? If you have a long gestation time, but you're in a danger level, is that going to act differently than if you had a short gestational time and were in a certain danger level, right? So this is going to make our model summary a bit crazier. Okay. So we now have gestational time, but then we have it also interacted with the 4 categories. And here in a minute, I'll try, if you've got time, to explain, okay, why does category 1 get omitted? Right. Again, it's used as the baseline here. However, see that a couple of these are not significant, right? Not significant, not significant, but a couple of them are significant. The R squared has improved. So maybe there's something to be said about the relationship between gestational time and danger level that changes the amount of dreaming sleep that an animal would get. Okay. This is not like a home run of an interaction term. Interaction terms usually aren't a huge home run unless you have like a really good reason to suspect why they might be there. All right. But this is still an improvement. All right. The predictive model ability of the model has improved, right? So our R squared is, well, I'm going to say the adjusted R squared is 0.585 or 58.5%. Right? We don't have to interpret every single p-value in our model results. It can be enough to say that gestational time is important, danger level is important, and that gestational time has a different impact on dreaming sleep for mammals that experience different amounts of danger. Right? So what is going on with gestational time? Okay. Well, again, going back to some of our intuition and thinking earlier, is it possible that it is really a stand-in for something different? Okay. Perhaps biological sophistication, animal size, right? It's not necessarily, and this is why we have to be careful about saying causality, right? The longer gestational time is not causing them to dream for longer when they're sleeping, right? But it's related to them dreaming longer when they're sleeping. And maybe that relationship really happens through some other lurking or confounding variable that we're not accounting for yet because we don't have it in our data set. We don't have like biological sophistication in our data set. We might have animal size. Okay, so we could explore that next. That might be where I would go next with some of my experiments here. Okay, but yeah, we've learned to improve our model, include more terms, and evaluate whether those terms have improved or not improved what's going on. All right. So again, one final word of warning: still be careful about extrapolating. Be careful about interpreting that intercept unless it falls within the range of your data set. Okay. As our data is still a sample and it still only speaks to, for example, mammals, right? And mammals with a similar composition to what we have here, right? Our long bones data set, again, does not apply to all burials. It only applies to burials with similar circumstances. So be careful generalizing to other things. Now that's kind of hard because generalizing is really our goal, right? Our goal is to learn from this sample and apply it to data we haven't seen before or other situations, other scenarios, right? I want to fit a linear regression that for my company that can forecast sales, for example, right? And next month, when new things happen, I have new customers come in, I want to be able to say, predict how much sales I'm going to have or something like that, right? So I want this model to generalize to unseen data, but I want to be cautious that the data I'm applying it to when I generalize is similar to the sample that my model was trained on. If not, my results might get wonky, and I might trick myself. I might mislead myself into thinking my prediction's saying something that it doesn't. Okay, so really, we're going to see this is the ultimate goal of machine learning: to train on data that we have and have it work on or generalize to unseen data that we're going to collect in the future and have it still perform well, right? So extrapolation, using this model on new data points, all these things are kind of can be a little bit dangerous, but if we've been careful about the context in which we collected our sample, then and really know what our population is, then we can safely generalize some of our results. So the last thing I want to show you, we have 6 minutes left. Okay, I want to show you a little bit of what's really happening when we use that categorical variable indicator, the capital C in the parentheses, and why one of those columns gets left out of the model summary output. All right, and this is going to have to be a little bit fast. Okay, and I'm going to make a fake data set here on my personal account, but that doesn't matter. Okay, so imagine we had a data set that included as an X variable something like eye color. Okay, and we might have blue, brown, green, another person with blue, and another person with blue, another person with brown, right? These are individuals, right? And what is this variable? Well, it is categorical, right? However, it's in string format right now, right? So one thing we're going to talk a lot more about Unit 2 is how can we take categorical variables that are represented with strings and turn them into something numeric so that we can work with them? Well, I might say that, well, one way to do this, and this is what our regression model is doing right now, is through a process called one-hot encoding. Okay, this is what happens whenever we include that C and say that, hey, treat this as a categorical variable. What's happening is that each of these different categories gets a new column, right? So this is how my data is in my data set. And over here on the right, let me put in get this to go away, a little bar here so you know this is different, right? My data here on the right is what stats models actually turns my data into. It's actually doing some data transformation behind the scenes for us. Okay, it's going to make a new column that says eye color blue, and then eye color brown, and then eye color green. Okay, for each category, right? Notice I've got blue, brown, green, and I've got 3 categories over here. And then what stats model is doing with this one-hot encoding behavior is it's creating indicator variables, right? Oh, say, so in this column, is eye color blue? Yes, it is. Well, and then this one's it's brown, so it's not blue. Green is also not blue. Well, then we have blue and blue again, and then brown is still not blue, right? So we have a 1 every place where the eye color was blue, and 0s for both green and brown. Same thing with brown. Well, blue is not brown, brown is brown, green is not brown, blue is not brown, blue is not brown, brown is brown. Okay. And then last but not least, we have eye color green, okay? But without looking over here on the left, pretend that this is gone. I'm going to delete this column, okay? Can you figure out if the eye color is green without looking at the original column, right? If I know that there's only 3 categories, possible categories of blue, brown, and green, well, if it's not blue and it's not brown, then it has to be green. That's the only option that's left. Right? And then for all these other places, I know, well, it can't be both blue and brown, so it's 0s everywhere else. Right? Okay. So this is, well, I'm going to have to do Command Z a bunch here to get my column back. Okay, but we'll do 0, 0, 1, 0, 0, 0. This is what stats models is doing behind the scenes. Okay, it's taking our categorical variable and it's actually splitting it up based on its categories and creating multiple X variables. This is why we get a different row of output for each of the categories in the stats model's output. However, one of these gets left out. Okay, probably the one that is the most common, like eye color blue in this example, might get omitted from the stats model's output. And then the coefficient for eye color brown in the stats model's output would be relative to eye color blue. Now, I don't know what we would be predicting here, right? But whatever one gets omitted would be our baseline, okay? And then the coefficients on the other two would be relative to the omitted column as the baseline. So we saw this with the danger levels, right? Right here, right? We only ended up with danger levels 2, 3, 4, and 5, right? Because danger level 1 got omitted, right? And then these coefficients are relative to being in danger level 1. How much less sleep do you get than the mammals in danger level 1? All right. So this is why one of those categories is missing. All right. And really what's happening behind the scenes, we're going to learn, this is a method of what we call categorical encoding. And we're going to learn a lot more about categorical encoding in Unit 2. There's actually a few different ways to do it. One-hot coding is probably the most popular way of doing it. But what's the problem with one-hot encoding? It's creating a lot more X variables. Okay. So we may run into challenges with the curse of dimensionality if we one-hot encode, right? If I had a categorical variable in my Longbones data set that had 10 categories, well, then I would essentially be creating 10 more X variables, right? I would be I would be approaching the level where the number of X variables in my data set is equal to the number of rows I have of data, right? And I'd be in more of a risk of overfitting and all those things we talked about. Okay, I just wanted you to know that that's what's specifically happening behind the scenes when we use that categorical indicator, and that one of these columns gets omitted also to avoid collinearity, right? Because we could determine the green eye color with just based on the other two, right? This last column really isn't telling me anything that these two columns haven't already told me, right? So after I control for blue eye color and brown eye color, the last category doesn't really tell me very much, right? Similar to how when we controlled for gestational age, lifespan didn't tell me very much. Right? So this is just one, this is a little bit more advanced reason, but this is another reason why that one column gets omitted from the output. It's because we really don't need it. With just knowing blue and brown, we already know everything we need to know about green, right? Because I could determine it based on the other two. Okay. So that's a little bit complex, but that is just a very brief example here of one-hot encoding. And so don't be worried, don't be concerned if you don't see all of your categories out here. There will always be one that is omitted, and then these coefficients are in relation to that omitted category as the baseline. All right. Okay. Any final questions here? Okay. Oh, yeah, and Curtis and Chelsea having a good discussion in the question thread saying that I've been talking about dreaming sleep the whole time. But slow wave sleep is non-dreaming sleep. Parasleep, paradoxical sleep, is dreaming sleep. So if I've misspoken here or used the wrong one of those, sometimes I don't keep them perfectly straight. So
no, you hadn't. I had read it before, even when we were first had seen this, but I forgot. I guess it locked in like para is kind of one of those. That's why she said it's non-intuitive. You'd think otherwise. So. I just hadn't gone back. I didn't want to break away and go look and say, what was that? What? Wasn't parasleep the other one?
Yeah, why can't scientists just name things normal things? No, I don't know. They have their reasons. So, okay. Again, getting more complex here, doing some hopefully more interesting things with our models, adding more X variables, makes things more complicated, but we can now fit the data better. We're going to generate better predictions. We can look at more complex relationships in our data, right? So we're getting more advanced, and I hope that's exciting. So thanks everyone. Have a great lunch, and we'll be in touch through Slack and any other means we need to answer questions throughout the afternoon. Thanks, guys.